A question to Len. Do you know when the presentation is being recorded?
Sorry?
A question to Mr. Julian Len.
Hola Ángel, ¿me escuchan?
No,
Sí,
no está ya bien.
Ahora sí, ok. Nada, muteo, era para saber si andaba el audio nomás.
Hello.
Hello Ángel. Hello Wolf.
Okay. This talk is the second talk in a series about our Ethereum-like node implementation. The first talk was also recorded. I am recording this talk too. This time, the two main topics to cover only 1 hour are the way that our node is communicates with other peer nodes, the message they interchange, and the block processing. Maybe in the next talk we will cover transaction processing and other topics. But the idea to grasp today is that a node, I usually say a node instead of a Ethereum-like client. Our node communicates with other nodes using TCP interchange with some messages that interchange with other peers that are based in the Ethereum wire protocol, but it's not the same protocol. So our node can only communicate with other similar nodes. If you know, there are an ecosystem of Ethereum clients, wallets, application, dApps, and and more. And those applications can communicate with our node, but our node can only communicate with other RSK nodes. It cannot communicate with other Ethereum nodes because we changed some years ago the message format, and we added some special message in the protocol. When the node started, if you read the instruction, the public instruction how to run the node, it started with a Java class that is the start. Let me show the class. The start class is instruction free. Sorry, here. The start class is the start of all the work in our node. And the main things to notice now is the start is a main static method in Java. But the main thing to understand now there are two classes, the context and the node runner. Notably, the context is a bit large. If you see if you read the code, and has many objects that are referenced at the beginning, because these are the objects that we are using in the running of a full node. There are many things to cover and to understand. To me, it's a bit large. We could refactor this in a simpler way, but really is something that it was in some way inherited from the original Ethereum Shell code. But the idea of this big class is to create the different objects that are needed to run our node in a way that they are in some way singletons. For example, there is a method get blockchain here. This is the method that create an important class in our node, that is the blockchain. We will discuss this class today. But then internally, it's only created once. Notably, is involved not only the creation, but also the load or something from Dix at the beginning. But for example, get blockchain loader is a helper that is created here only once. If already created, the same object is used. But it's very common in this code that every new object that we need, the helpers object that the new object needs are injected in the constructor. The constructor has all the logic to inject the helper object. For example, in this case, something that is called the transaction pool, and the transaction pool is created here, and there also is created only once, but this transaction pool is created using more and more helpers. For example, the block store, and the block store is created here. The block store is a LibelDB database that resides in a database there that came from the configuration, and so on. In short, there is a lot of objects involved running the instance of our node. Maybe we should refactor and simplify this code, but now it's in this state, and maybe it's a bit overwhelming, but it's working now. Initially, all these objects were injected using a Spring Framework, and so the Spring Framework was used adding object and object to other object using annotation like AutoWire or AutoWire and similar annotation. But at the end, it created a mess of objects. We have a lot of objects now that are interlinked, and maybe we should review this implementation. But now is what we get. Okay, back to the slide. The node can communicate with other node, because at the beginning, each node when they start communication with some nodes that are called Bootstrap. Maybe you already know that name. The Bootstrap nodes are defined in a configuration file for each of our network, mainly mainnet and testnet. The node communicate with the Bootstrap using, as far as I know now, using UDP. So if you haven't UDP ports open, maybe you cannot communicate with the initial nodes in the network. The bootstraps, where are defining the bootstrap for each of these nodes? Well, maybe I have here, sorry, here, I have a configuration for the main. There is a configuration file defined for mainnet. Here in the section in the configuration peer discovery, there is a list of Bootstrap, initial Bootstrap. The Bootstrap are maintained by the DevOps group in our company, and this list is related with mainnet. There is another list of Bootstrap node for testnet. The local node or the standalone node, we name it Vectest, has no Bootstrap node. It runs alone. You also could define some initial peers in the configuration file, but now I don't have any example, but you could add the initial node to communicate in the configuration file. But then when they started to communicate with the Bootstrap, what is the mission of the Bootstrap? Well, the mission of the Bootstrap is that once the node communicates with the Bootstrap, the node informs the Bootstrap that, hey, I'm here, I am a new node in the network. And then the node asks the Bootstrap, give me a list of peer nodes. The Bootstrap gives the node a list of peer nodes, and the node started to collect those peers. To avoid to connect to all the network, Bootstrap only gives to each node a limited list of peers. The list of peers are kept in the Bootstrap. The Bootstrap communicate between them. They share that table of known peers using what it could be called a distributed hash table based on Kademlia algorithm. And then each Bootstrap informs the new node, some candidate peers. In our code, the candidate peers resides. Sorry, where is my code? In the Peer Explorer. Peer Explorer class has a list of known peers for the running node. The Peer Explorer has, in some way, is a thread that start conversation with other nodes that are provided by the Bootstraps, and then connect with other nodes. You cannot connect with other nodes without knowing the other node public key. So if you know the address of the other peer in the network, you cannot communicate and connect with that peer without knowing the public key of that peer. In order to avoid spamming the node with other softwares, with other running nodes. The public key are kept by the Bootstrap. When a new node announces its existence to the network, gives the public key, its public key to the Bootstrap or one or more Bootstrap, and then the Bootstrap provides the public key and the address of that node to other peer nodes. And the handshake, there is a handshake in the peer-to-peer protocol that verifies that the public key is right, that verifies that the other node has the correspondence private key. Any question so far? Okay, sorry, I need to read something here. I don't know where I have a list. Okay. For example, how the Bootstrap gives our node the list of partial peers, a partial list of peers, because using the Cademlia algorithm, each node has in some way a unique ID, and the Bootstrap algorithm gives to the node the other peers that are near in a matrix to our new node. This is the responsibility of something that is called node distance table. The node distance table allows to having a new node give a list of nodes or peers that are near of the node in a invented metric. It's not related with physical metrics. It's not related about the geographical location. It's only a metrics about how the distance between the unique ID of the node to the other nodes' unique IDs. But this is part of the code to the given, for example, a node ID. You can obtain a list of nodes that then are sending from the Bootstrap to the new node that connect to the Bootstrap. The Bootstrap, oh, I forgot. The Bootstrap are nodes, are like other nodes, but with this functionality activated to keep and to distribute a shared distributed table of known peers. Okay, the peer explorer, and then when we communicate with other node, I say that the other node is communicating with other node using TCP, Transport Control Protocol. We are using a library called Netty, a Java library, very known Java library, communication library. Our Netty communicates with the other peer given the address. It opens a socket channel, in this case, non-blocking input-output socket channel. And our code, the original code modified by us, is the Ethereum channel initializer. What is the responsibility of this class? Let's go Ethereum channel initializer. Well, it's something that extends from for some class from the Netty library. And the idea is to have of this class, the responsibility is to giving an input, a new socket channel established with the other node, start to manage the handshake, start to control that the other node is valid, start to ask the other node its capabilities, and then if all is okay, a new object is created that is called channel. Channel is something that was created by the Ethereum Share people. Is the way that we have to communicate with other peers. A channel can send message and can receive message from other peers, but this is something that we wrote based on the Ethereum Share implementation. The channel usually these classes are not usually modified frequently because they were created many years ago. But the responsibility of the channel is to have to to manage the incoming message from the other nodes. I don't know if here is here, but I guess that is, sorry. The channel. You know that here is a message queue. This is the class with a strange name, maybe, that is the handler of the incoming message, the wire protocol class, whose responsibility is to receive a message from the other, what is called the Ethereum message, and then attend this message from the other peer. These Ethereum messages are not are the base message that we inherited from the original code. It's here, but at the end now we have something new that is here. Each message originally has a type. In this case, it's called the get command. Returns the type of the incoming message. But the new thing is that we have a dedicated type for our message. In some way, the original message was lost because now our messages are like a letter in an envelope inside the original message. The original message is mainly has frequently this type, and this type has another message inside. You can notice here. You have another message inside, and that message has different types. We will discuss some of the type of this message, but at the end, the important thing to know are that these incoming messages are posted, are not now processed, are posted to the message handler. On the message handler, the only implementation is here, the message handler that implements all the logic, all the logic is called the node message handler. This is our class that implements the message handler. And the idea of this, this method is to put the incoming message in a queue. Why? Because originally the message was processed directly in the channel, but we suffer some problems with the time of the processing message because sometimes in our early days the message the process of the message employs a long time, and then we lost the communication with the channel, with the native channel of the other peer. So we decided to have, in some way, a back pressure control using a queue. We should discuss maybe if this queue is totally the best solution, but now we have an incoming message queue. Sometimes our node, some nodes have problem with this queue because this queue is filled with lot of messages sometimes, because some messages could employ a lot of time, and then the queue could be filled, and then the node could crash. It's a problem we are working on this. We are exploring different solutions like priority queues. Maybe we should explore to process the message in different consumers, not only one, and so on. But this is something under development. But if someone of you are DevOps, maybe you know that one of the issues that sometimes appears in a running node is that this queue is filled with maybe thousands of incoming message. Okay. Sorry. I am connected, yes. Well, when the Ethereum channel initializer creates all the channel and what is the channel, there is a class in our system that collect all the peers. All the peers are kept in an internal list in the channel manager. The channel manager is a very important class in our implementation that has all the information about the other peers. We have also some issues here because if we read the logs of a node, the peers appears and disappears, and we have many connection, reconnection, disconnection, and reconnection, and we should explore which are the reasons to such behavior. But there is something that is a known issue in our implementation. Okay. Then the Ethereum message is transforming our message, and then which are the messages that we can manage? Well, we should visit the message class. We were so young creating this class some years ago. Then this class is implemented. Oh, sorry, where is? It's implemented for many of these concrete messages. For example, blog message. Blog message is the message that communicates a blog from one peer to other peer. Sometimes one peer requires a specific blog from other peers, and then it could send a blog request message. Sometimes we require not the full blog, but only the blog header. There are messages to request blog headers. There are messages to inform, to communicate to the rest of the network the new blog hash message, that there is a new blog without distributing the content of the blog, only announcing the new hash. And there are many, you know that there are many, now you can see there is a transaction message with the list of new transactions logged by other peers and so on. This is the class we must master to understand the wide protocol within our peers. It's not hard. Mainly are status message, blog message, transaction message, and some request response message like give me the blog, inform me, I inform you a new blog hash, and so on. It's not really overwhelming, but it's a bit long only. Most of these messages were discussed in security issues. For example, we retired some messages that could be sent and provoke spam to the other peers, and we should take care of this kind of message, but now are under control, at least by now. And the message process, I say that all incoming message goes to a queue. The queue it resides in a message handler. Recently, the message handler has a thread, only one thread that consumes the queue. Maybe one of the things that we could try is to have more consumers to paralyze. I don't know how to say paralyze the process of incoming message. Maybe to paralyze the process of blogs and the process of transaction separated of other message. But now we have only one consumer. Maybe this is a possible bottleneck in our node processing. Some months ago, a message visitor was added that I don't know really why it's called visitor, but it's not exactly the known pattern implementation. But the message visitor is the class that distribute the incoming message to different participants. Let's go to node message handler. It has internally the queue. Any question? Okay. Sometimes we have here a control that repeated messages are not processed. We should discuss in security issues and performance issues about this control. Sometimes some messages expires by time. This is the main code that pull the queue and process the message, the new incoming message from the queue, usually using the message visitor here that is created for each incoming message. Maybe it could be improved this. And the message visitor has some helpers that are important in our discussion. For example, there is a dedicated option called block processor that, as you could infer, will process the incoming blocks. The SIM processor is a bit more big because it has more responsibility as synchronize the node with other peers. If the node recently started and need to know to retrieve all the blockchain, the SIM processor is in charge of that communication. Transaction gateway process, validate, and distribute the incoming transactions. There is a peer scoring manager that is not really totally used now, but we are planning to have a score for each of our known peers, so we could resist some attacks or detect some bad behavior in our peers. And the channel manager that knows all the other peers sometimes is used to relay some of these messages. For example, if a block comes to our node, it could be processed by the block processor and other processors, but at the end, if the block is valid, we should relay that block to other peers, to other known peers, and that is the responsibility of the channel manager. Also, the message visitor receive the sender. Why receive? Which is the sender? The peer that sent the original incoming message. Why it received the sender? Because, well, for example, it could annotate the scoring of that peer, and also when the block is valid and should be relayed, maybe we should avoid to relay the same block to the peer that originally sent the block to us. That is one of the reasons to have the sender, the channel manager, the block processor, and so on. Well, the message visitor is maybe the only thing it has many different methods for different messages. For example, the block message is processed here. The status message is something that other nodes constantly send to our node. This is something that is, as far as I know, or as far as I remember, is not in the original Ethereum implementation. We added to repeat the status message only for convenience, but I guess that in the original Y protocol, the status message is only sent at the beginning. But now in our implementation, we send the status message, I don't know, maybe 20 seconds to other peers, only to keep the bit of communication and to control if our node is is out of sync of other nodes. Okay, that is the other interesting class to explore if you want to know about the message, incoming message processor. Back to the slide. In case of the block message is sent to the block processor. There are other messages that are sent to the sync processor, and the transaction messages are sent to the transaction gateway. But let's go to discuss exactly the block processor. I came to the block generation in a moment, but first here. When when there is a block that is coming from other nodes, is received by the message visitor, and notably, the message visitor send the block to the block processor. But there is a surprise. The block processor send the block to a sync processor. Something that is maybe was coded 1-2 years ago, because originally the block processor was in charge of all these things. But now block processor has some do some check-ins and then gives the block to the sync processor. And at the end, the sync processor gives the block to an important class in our implementation, that is the blockchain. There is a blockchain implementation that has a block validator, validate the block, execute the block, and then decide if the block was executed in a valid way, update all the storage, all the account states, and then if all is good, the block is saved in a database, a key value database that we call the block store. Blockchain implementation is the class that implemented blockchain, and maybe it's one of the most interesting class to know, because the class knows the previous block, knows that if this block has a parent, and the parent should exist before this new block processing. It knows about the account state, it knows about the contract storage, and so on. It's not a long class, but it's important because it has many helpers that allows the execution of the block. Sync processor has many other duties, like to know the state of other nodes, and if other nodes has better node than our node, better blocks. For example, the sync processor started to ask the other nodes, the other piece, please give me the blocks that are needed that you have and I don't. But there is an algorithm to synchronize. We call this the long synchronization algorithm, and now it's a long process. Maybe I'm not sure, but maybe if you start from zero, the long synchronization with mainnet could employ maybe 1 week. I'm not sure now what is the time. Well, if all this is good in the case of block, the message visitor communicate with the channel manager to broadcast the block. There is an issue to me, in my opinion. There is an issue in the message visitor and the channel manager, because if I go to the message visitor, go to the process of the block, is here, the block message. Process check if the block is too advanced, or if it not had some information, but then give the process block to the block processor. And then if the result is an invalid block, only record the bad event. But if the block is valid, try relike the block. What is this method try to relike the block in which way? Well, you know here is the channel manager, but it's not broadcasting the block. It's broadcasting only the block hash. Is the broadcast to of the block hash of the new block.
Angel, sorry.
Yes.
Here we have Pablo has a question. We are all together in the same room.
Yes. Hi. So it was about the node message handler class you were presenting to us minutes ago. So there is a method there, process message, that is synchronized. My question is, why is that method synchronized? Because it seems to be invoked only from that class inside the loop. So a priori, I don't see any parallel invocations of that methods that will require synchronization.
Okay, I agree with you. I don't know why, but because of all the many of these things are only consumed by the only consumer of the incoming message. But yes, there are some process that could be called for different parts of our node. For example, we could share some method execution from the JSON RPC method. For example, there is a JSON RPC method that is called I don't know how to say in English, ETH call, that is call a transaction. Well, that method invokes at the end the same object that the blockchain or block executor that are behind all of this code. And then in those objects, we need synchronization logic. But in others one, we really don't need, but maybe it was added only to planning to have more than one consumers or something alike. We should review each of the synchronization things.
Yeah, but in the case you mentioned, unless the other alternative path that ends up calling process message is sharing the same instance, then synchronization is going to have no effect. I mean, if the JSON RPC call use a different instance of the node message handler, then synchronization is pointless. I mean, it's going to execute in parallel with another node message handler, right?
Yes. The message handler is only consumed once or for only one active thread, but maybe the block for example the try or no, not exactly the try, but other for example the try key mapper has some synchronized method. I think that this method could be removed also, but now they are marked as synchronized, maybe because we are afraid that could be called from different threads.
Okay.
We should review that all this. One of the problems we have now to implement many consumers from the same queue is that we need to take into account synchronization issues very careful. I want to have a node that can manage synchronization out of the box, but sometimes it's hard with the current code.
Okay, thank you, Angel.
Okay. Well, to me, this is a bit long process, but I depicted what a vocabulary. I describe this process, and then you could explore these classes and options. Well, but when a new block is generated, it's generated in the miners. You know, the miners create a new block using what is called the transactions that resides in the transaction pool. The transaction pool is something that all the nodes have, and is an in-memory list of pending transactions. Sometimes you see the transaction pool usually in the Explorer. The Explorer, the website, has a sector where you can see the pending transaction in that node, because each node could have different transactions in its transaction pool. But each miner is a node and has its own transaction pool. And then when a new block should be created, they take enough transaction from the pool to create the block. Remember that a block has a gas limit. You cannot add lot of thousands of transactions, because there is a gas limit to all the block, and that is part of the Ethereum protocol, to avoid to have a giant block in any case. And then this block is not related to the rest of the network. You know that there is a process called merge mining. I think that there is a Planet talk directly. I don't know if Lerner or some of the miner team will give the talk related with the merge mining process. But it's very interesting for our implementation, our company, because it adds something that the original Ethereum network don't have, that is the security of Bitcoin miners. I don't have all the knowledge or time to discuss all the implication of this, but in short, there are pool software that take the new Bitcoin blocks that are generated in a Bitcoin node, gives that Bitcoin block to other miners in a pool of miners. And then the miners try to generate a proof of work for that Bitcoin block. Okay, but what is the merge mining? Well, we have pool software modified to not only query a Bitcoin node to know the new block to mine, but also to query our node. Our node has a JSON RPC method where the modifier software pool asks our node, give me your new block, and then I will try to include the abstract, the block hash of that new block inside a Coinbase transaction in a new Bitcoin block. That is in short, the merge mining process is only a very, very short description, but that is the reason we have some codes like for example, we have a miner. It's called miner server implementation. It has a method called get work. Oh, sorry. Miner server have a method called get work, and this method is called from other part of our software, and it gives the new block to mine. This method is called from the miner module implementation that exposes a JSON RPC method that is the get word. The get word is a relatively standard method that are used by the pool software. The pool software query using JSON RPC our node to get the new block. When the new block was produced by the miner pool, the pool software calls this other method is submit Bitcoin block. That is the other method that informs the new Bitcoin block that has the merge mining information for our RSK block. And then the miner server receives the new Bitcoin block to process. This is the process of this result. It checks that the merge mining information is good, add the new block and to the blockchain, and relay the block to the rest of the peers. I guess that we have a problem here, an issue, maybe maybe a problem here, because in our implementation, the creation of a new block, the get work of a new block for mining is only generated with a new block comes to our blockchain. That is maybe, to be confirmed, the reason why our testnet on mainnet, when you send a transaction, the transaction is not added automatically maybe to the next block. The next block should be produced, and then in that moment, maybe in 20 seconds or half minute, in that moment, a new block is produced and with the new transaction that you sent maybe half a minute ago. So there is a delay in adding our transaction to a new block. For example, in the issue description, there is code about the miner processing the Golang implementation get update the block to be mined when there are new transactions that came to the transaction pool. So they generate blocks and blocks with new transaction practically at the moment the transaction arrives. In our implementation, the block is only created when other block is mined. So maybe it's a delay between the arrival of the transaction, the inclusion of that transaction in a new block, and then to the mining of that block and relay to the rest of the network. But that is something that we should discuss. There is an issue, but well, we need to discuss pros and cons to improve and change that algorithms. Well,
Angel, can I ask you a question?
Yes.
And the pool server plugin that connects to an RSK miner, is that RSK miner node run by the pool server, or it's owned by them, or they are connecting to an RSK node owned by somebody else? How, in that case, how do they choose which node to connect to?
Well, I guess for interest of the miner pool, our node is run by the miner pool itself.
Okay.
This green node in this slide, RSK miner node, usually runs in the facilities of the pool company.
Okay.
Because that node knows the public key of the miner, maybe the private key of the miner, to add as the Coinbase of the block, to inform, yes, my mining pool generate this block. That is the main reason that the pool has its own RSK node.
Yeah, makes sense.
Okay. The interesting thing to discuss maybe with more time is, but you can explore the blockchain implementation class, is that the blockchain impl, that is the main implementation of this logic, has logic to detect to know which blocks are already known in the block store, and if the new block could be added to ones of the chains, maybe there are alternative chains, and all this code keeps all the valid chains. And in these slides, you can see that there could be many chains, alternative chains with different blocks. Also, there is something that we add. No, it was added in the original implementation, but we changed a bit. We also have a list of orphan nodes. Maybe a node that we arrive to our node, but we don't know we don't still know the parent block. The orphan blocks usually, I should review the current code, usually are not saved in the block store. They are only blocks that reside in memory. In order to, if the parent block arrives in some, maybe in few seconds, we don't need to retrieve or to request the child node to other nodes. The orphan node resides in memory only for convenience. If a block arrives to our node and is orphan, is kept in memory. There is a list for orphan blocks that are added when the parent arrives. When the parent arrives, maybe there is a domino effect, because maybe the parent of this node arrives, and then the incoming block is only one, but there are 2 blocks that are added to a blockchain, maybe 2 or maybe 10 blocks, because maybe there are many orphans in a chain. Then we added the logic to manage that case. Maybe we have sometimes there is a method informing, yes, I added this block, but the method returns the list of blocks that are really connected. Maybe there are more than one in the process. Well, I guess that is the end. We should explore transaction execution and virtual machine the next talk, but I guess that we cover all the today topics. Any question? I give this talk not in Spanish, not in English, but in English. That is Angel English that I hope that you could understand.
Good, very good. Thank you, Angel. Very good.
Well, I will stop the record.